today we're gonna cover a really interesting paper, a simple, nice paper, very useful and impactful, and honestly, I just enjoyed reading it all in all. And while this might not be the biggest breakthrough, if you are interested in building agents, this is definitely a video to watch. And if you really want to dig deep, definitely a paper to read. And I believe with this, if you're already building agents, you can build even more sophisticated, smarter, and more intelligent agents just by a deeper understanding on best practices and methodologies other researchers are trying to deploy and test that are proving that such methodologies can actually increase and enhance the performance of the agents that you are building. If you are not subscribed to this channel, please consider hitting that subscribe button, especially if you enjoy the content as we go through it. If not, consider hitting that like button for the video. And with this and without any further ado, let's get started.
Subscribe to Daddy's channel. The mic.
Okay, so this is the paper, Fundamentals of Building Autonomous LLM Agents. And this is my first paper to read that is done by researchers in Barcelona, Spain and Munich, Germany. So basically they are in Europe. So hopefully Europe is trying to catch up now with AI research. Fundamentally, what this paper is about is they're reviewing the architecture and implementation methodologies of agents powered by LLMs. Now, what they say that the motivation of this paper and doing the research is the limitations that they see in large language models in real world tasks and how actually using agents with these LLMs or giving those LLMs agentic abilities will improve their performance across the board. Now here they're putting forward an architecture that uses elements like a perception system, a reasoning system that works with things like chain of thought or tree of thought, and then a memory system that works around short and long-term memory, and then an execution and validation systems, things that will get tasks done and validate the outcome of that run of the agent. And fundamentally, they show when all of these elements come together, this agent or this agent architecture can actually mimic highly human cognitive processes for autonomous and intelligent behavior, improving the performance of agentic LLMs as they are enabled with such architectures and tools. The reason I like this paper is they are on the side of vibe coders, I think. So you can see here they are saying we are closer than ever to realizing the idea that if you can think it, you can build it. Basically, this is the idea of leveraging AI to build stuff. So vibe coding in concept. Instead of relying solely on programming skills, what increasingly matters is understanding how a human would reason through a problem, since LLM agents can learn and mimic human problem solving by externalizing intermediate reasoning and refining it through self-feedback. So again, the goal is to get agents to think like humans, to get to a point where you can say, okay, if you can think it, you can build it. Basically, if you talk to such an agent, they will be able to think through a problem, solve it, remember what they've learned, reason around that, maybe reflect on it, and actually get to build things better. And here they say something interesting, that the transformation we are going through with agentic LLMs or agents in general and all of these systems really is still in its early stages, which we know. The whole AI revolution, if that's the right term, happened actually around 2 years back. And that's it. Everything you see around you is 24 to 36 months old only. So we are actually in the early stages. So engaging with LLM agents is comparable to engaging with a new species, one that we are only beginning to understand, train, and guide. So this is a really interesting way of looking at it. We are dealing with a really new species that we are developing as a human. Digital species or entities, as per Karpathy, ghosts of humans. So things that mimic humans for now, but we can actually convert them to something else maybe in the future. Fundamentally, the question they want to answer, or they're asking here, how can we build agents who think and act intelligently? How should we structure their minds so that they can interpret information, reason, plan effectively, and make decisions that we can trust? All of these are fundamental questions we need to think of while building agents. And here they have clear objectives for this research. And it's linked to the question that we just asked. How do we build these type of agents? And they have very clear set of goals that we will go and cover in detail as we go through the paper. And the first one revolves around perception systems, which we'll cover later. And this is fundamentally the eyes and ears and senses of the agents. And then examine the reasoning architecture. What is the best way to approach reasoning? Is it chain of thought, or is it a tree of thought, or something else? And the third goal is, how do we explore or evaluate memory in general? So memory is one of the biggest challenges for LLMs and for agents. And here they're talking about things that you've heard of probably, like RAG, retrieval augmented generation, long-term memory system, investigating effective methods for information storage to enable practical and useful application. We as humans, to a certain extent, we have long-term memory and we have short-term memory, the context of a conversation or the context of something that you're working on now. Not all of that gets registered in the long-term memory of our brain. How do you actually structure that around the agent? And even for us as humans, we augmented our brains with outside memory. So all of the Google Drive or the tables that you use on a daily basis, I think that can be considered human augmented memory sources, where we go in, we use our own perception senses, which is our eyes, to read through maybe information that we stored for long term. Okay. So examine available execution architecture, such as tool-based frameworks and code generation approaches, exploring their contribution to automating tasks. So how do we go about implementing tasks? What's the right way to do it? How do we get high performance or high accuracy in the task being performed from the goal, or when the agent ran code through the orchestrator to try to trigger a function or some other tool that it has access to. And then all in all, they wanted to evaluate the complexity of implementation of each system solution proposed. So they're looking at everything here, and by the end they're going to have a kind of a big picture look and see, is it too complex to implement? Will it have issues? I presume here. Now here they actually understand that there are limitations and challenges beyond the problem they're trying to solve. So in this nature of agentic LLMs that they're talking about, these are LLMs to be considered smart. They need to perceive a wide range of information or information mediums. So they're saying here, they're starting off the bat by saying there is difficulties in GUI, which I guess is graphical user interface, grounding, and operational knowledge. And they're saying that agents struggle to accurately map screenshots to precise coordinates for their action and lack of deep understanding of basic graphical user interface. So whenever the agents are interacting with information, their best source of information, other than the API calls for making browsing information from the internet or getting browsing information from the internet or something similar, is actually taking screenshots, because not all services out there on the internet has API access, and some of them is simply just accessible through the screen. This is how we humans built the internet. Again, one of the other challenges is the repetitive task. These agents, when you train the large language models, they predict repetitive action, indicating a lack of progress or an inability to break out of loop. So if you want an agent to be smart, it shouldn't be just going through the same action it keeps doing in the past, or it was trained to do as it was developed. You need an agent that hypothetically is able to decide on new ways to create actions or new actions out of thin air, based on reasoning, based on information and tools it has, and implement or execute those. So that would actually be a feature of such agent structures or architectures that will be considered as advanced or smart. Again, one more thing around user interface. Here they're saying inability to handle unexpected window noise. So when the agent is looking at a tricky visual type of window, I'm assuming it can actually, like here, they're putting here unanticipated pop-up windows or dialog boxes, actually that can set off the agent and it will confuse it. So this is as well one more limitation these agents today that we have face and struggle with. The fourth is again something related to the user interface, and this is limitations in exploration and adaptability. So here they're particularly talking about agents equipped with modules like set of mark. So set of mark is kind of a library or the ability to work with or read the containers that are available on a window or a web page. So the agent is able to tell which container is actually marked for what exactly. So this will provide the agent with some information, but also this will have lots of constraints and limitations for these agents. Fundamentally, there's the core of all of that, in my opinion, is the significant performance gap with human capabilities. There was a recent study done, if you're interested, write me a comment in the comment section, I can add the link for it, where actually they gave some agents real-world problems and the results were shocking. Again, I'm talking about problems where humans will do quickly from A to Z across different stages of reasoning and actions. Nothing that we consider as humans as rocket science. The best of agents actually, or LLMs, failed miserably with a very, very low success rate. Again, the performance gap in a real task completion is very big. So still humans lead the way, believe me. These agents, if you're outside the bubble, these agents are way behind to the level that they threaten significantly the careers of humans and the abilities of humans. We're not there yet. This is a problem, again, the paper wants to improve, because having those agents actually do things for us reliably might make our lives better as humans, even in career. So these are the challenges on top of the problem they're trying to solve that they're expecting to face. Okay, I will not cover this part, but it is interesting if you are just getting your toes into the water when it comes to AI and large language models. They were generous enough to cover that. I've never seen that before, someone covering the background. And if you read it, it's made for anyone actually to enjoy reading this paper, which is smart in my opinion. But go ahead and read it in the paper. This is some background on large language models, talking about the transformer and the architecture, neural language processing, and so forth. And also, if you go down here, you will find something related to what's the difference between a large language model and large language model agents. If you want a deep dive, I have a video on my channel where I actually dig deep in the definition of agents and how they work and what they're all about. So there's a video for that if you're interested. Even they go through the workflow versus agent. So if you're into automation, you understand exactly what this is. An agent is different from a robotic process automation or just a flow of automation of steps that happen sequentially and conditionally to achieve an outcome. This is totally different, and here they define the difference. I think it's very important, again, if you're new to AI and automation, it's very important to understand the distinction and the difference between the two. Now here we're gonna go into the interesting stuff and the building blocks and what they call the constitution of an agent. So we're gonna look into these systems. I'm gonna actually cover them as a concept. We're gonna look at some of the architecture drawings that they have, the high-level ones, and I genuinely recommend that even if you get the idea from this video, you spend some time to go through the paper and read it for yourself, because what they do in this paper is that they break down each of these systems or blocks one by one in detail. And I will show you a hint of what they cover, but I will not go deep in each one of them. The first thing is the perception system. So think of it as if you want an agent to operate like a human. Humans have lots of senses. We have sight, we have hearing, we have smelling, we have touching through skin, and we have other things that could be considered as pieces of information generating sources for humans, directly or indirectly. So we have so many ways to interact with the world around us. Now, you would want for any agent to be considered smart to have even something even remotely close to what humans have. So you want these agents to have some kind of a perception system. Now, for agents, perception system, the basic one is text, which we have. They can read text. Now, a step beyond that is sound, image, and video. So these are three mediums that could improve the ability of these agents to interact with the world around them. It's not even enough to replicate what humans have in terms of understanding the world around us. This is why they keep talking about world models for these LLMs in the future. But for now, when we build an agent, I want an agent that can see videos, watch videos online maybe, read text, look at image and understand that image. So all of these systems need to be built into the perception system of that agent. So regardless of what the agent comes across, especially online while browsing, it is able to actually perceive, understand, and later on use. Again, remember here, when that agent is looking at the video or an image or sound, each of them will be tokenized differently. Each of them will go into different embeddings. Eventually, the LLM should get tokens that to a certain extent give the LLM an understanding of what it's looking at, watching, reading, or even listening to. So this is the first and core concept to really develop for a high-end intelligent agent or agentic LLM before looking at any other system for the agent. Now, the second system is the reasoning system. And this is giving the agent a developed brain, a human-like brain to a certain extent. I don't think we can make such a claim. But this is a system that will offer tools or methodologies or logic fundamentally for the large language model to break down problems, plan things, execute plans in sequence or parallel, validate things, make reasonable decisions on what makes more sense or less sense, use ideas like consensus of multiple tries, and so forth. There's so many things in this world, but you need a system that will give the model different reasoning methodologies that it can invoke or use when it's trying to solve a problem. That would give it higher intelligence to deal with all of the information it is getting from the perception system. And it needs to do it in a way that is robust and scalable. So now we have an agent with senses that can reason with a developed brain. Now we need to give it memory. And here, memory is having multiple uses. This is not just for the sake of asking it about previous conversations. If an agent has memory, it can actually learn from its mistakes. It can actually record feedback from the users. And potentially, hypothetically, if you want to go really complex in these agent builds, it can actually train itself at some point from the memory recollection of interactions it has with users. So memory is one of the most important things and one of the frontiers of large language models and AI in general. And I think this is one of the biggest areas today companies, AI labs are competing to really improve on. Because if you have a large language model that is smart and can really manage long-term and short-term memory really well, it will bring a different level of experience for users when they interact with it. Lastly, we have action systems. So this is the tools, the APIs, the environment that the agent can use to actually run real-life tasks. And this, in theory, is mostly in the virtual world, but it can go into the physical world when we have these agents actually mounted on robots. So that robot will use all of the systems of perception, of memory, of reasoning, and action to actually do physical tasks in the real world. And today we are looking around us and companies are coming up with these products. It's very early super rich adopters might buy these robots, but we are already there. And this system that this paper describes is a system that can actually be developed for such a robot to have an action system based on all other systems as well to do real tasks in the virtual and real world. Here you can see the simplest diagram for the architecture they propose. So this is the environment where this agent runs. And here you can see the top layer of this is the perception system that deals with different types of media that the agent can digest and then take to the reasoning system, where it can do next level type of reasoning using different methodologies or concepts that it will give it higher intelligence as a model. Also, it can interact back and forth with a memory system that you see here, which is adjacent to the reasoning system. And finally, there will be an execution system. So that execution system can be responding to the user through chat, can be actually clicks on a screen. So something like having the ChatGPT Atlas agent do something, the closest example at least, and then can be something in the physical world, actually getting a robot to do a task in the real world. Now, while I told you that I will not go into the breakdown of each of these systems, one thing I think is very important to cover here, and I am sure you will appreciate that we spend a little time on it, and this is particularly for the perception system. Now, they actually propose an architecture for that perception system that enable the idea that we've seen of a perception system that can handle multiple types of media. And I'll show you the architecture. It's very interesting, but you need to read this for yourself. And here it starts with a modality encoder. And this is an encoder that can deal with all type of different media, of images, video, and even audio. And it will use different encoders. Here they put an example of a convolutional neural network, a CNN, or a vision transformer. Again, all of these systems are put as part of this encoder to extract rich visual representation or audio representation, depending on the type of media being used. An input projector, and this input projector is the different types of embeddings that you have to deal with for different types of inputs. So regardless of what the agent gets, at some point, the proper embedding for the proper media type should happen in the input projector, so that when it goes to the large language model for each type of media, the outcome will be something that actually the large language model can understand. So after that, so we get the embeddings here for all types. We go into the LLM backbone. And this is where actually the transformer or multi-head attention happens. Again, this is for text as a concept, but very similar happens for the visual transformer and other types of architecture, very similar to the text one in concept, in theory, at the core for vision and audio and other things. But this backbone is where actually all of the number crunching and the logic crunching happens, and the attention is actually decided. So later on, the large language model will actually predict the next token or predict the outcome basically based on these inputs. And then, as I said a second ago, we get the output projector. Fundamentally, this is the opposite of the input projector. This will give different types of outputs based on the expectation by the agent or the user to, at the final step, maybe return the response in different medias. So the input can come in as text, but the response as audio. Actually, the input can be a video and the output can be text. So you need the input and the output projectors for that. So regardless of the media input or media output, the system can deal with both to generate what the user or the agent decided is the best way to respond. And finally, the modality generator. So in case the output of the agent should be voice, audio basically, video, image, it can do all of that. And this is the architecture. You can see here, this is the input. It can be image, video, audio, and it all goes into the modality encoder. It is the encoder that have all types of encoders. So you can see here, it has the visual transformer. It has all types of image, video encoders. It has all types of audio encoders. And then all of that goes through the input projector for the embeddings, so that later on it can go to the basic large language model backbone that has typically the transformer architecture. This is why you see the text directly coming here, because you don't need an encoder, a special encoder or a projector for this. It has its own standard type of embedding. I'm assuming this is how they built it. And then if it's text, you'll get a text output. But if it's anything else, then you'll get the output projector that will transfer back these embeddings into number values vectors that actually can be used later on by the modality generator to generate output images, videos, audio, and text is already done directly from the large language backbone. So you can see this is a very complex system that they're presenting, and we have systems already running on that. This is probably what you have with at least ChatGPT when it comes to the architecture of image and video. It doesn't happen all in the same model. At least we can say that about Gemini, by the way. You can get it to do images, you can get it to do videos. Sometimes it works just by asking the model, but sometimes in the options you have to select it just to have a smoother experience. You can go and read the details. There's so many things, especially when it comes to the perception systems, that really, if you are serious about building that kind of next level agent system, this paper will break it down for you, concept by concept, idea by idea, requirement by requirement, which is super useful if you're building something, and it's super easy to read, I promise you that. And before I leave the perception system, even they highlight issues that you might face in these systems like hallucination, latency in inference pipelines, context window limits. Again, these things might kill your context quickly, data collection, computational resources. So all of that are things that they talk through while trying to develop the concept and the architecture for such an agent and for such a perception system. Now, the second main thing here is the reasoning systems. And without going through the details, what they propose here is that you need to equip your agent with multiple methodologies of considering a problem, breaking it down, planning to execute on it, validating the responses that the agent or sub-agents are generating, and how to actually conclude from point A to point Z when it is ready and safe for the agent to actually respond or to actually take action or execute on the thought process or the reasoning process of it as an agent. The easiest way to show you what they're talking about when it comes to reasoning system is showing you this visual for comparing different types of planning frameworks. Okay, so you have the basic one, which is sequential decomposition planning. So it will go for breaking down the problem into subtasks, and it will go through each subtask, create a plan, and then look at all sequentially through the plans and put it together in a final plan of addressing that problem. Now, a different type here, or a similar type actually, is interleaved decomposition planning. And here it will go actually subtask by subtask, and it will do the full job for the subtask and then move for the next one. While here, if you notice, it developed the subtasks early and in parallel. So you give it a problem, it will say, okay, this is 3 subtasks, this is 1, 2, and then 3, and then it will move sequentially in the planning process. Here in this type, the whole thing is sequential. So it will go, develop the first subtask, then do the first subplan, go back to the second subtask, then its subplan, and so forth, until it puts it all together for the main problem that the agent got for a final plan. Now, what they keep recommending here is a new methodology that they call DPPM, which is decompose, plan, parallel, and merge. And here it breaks the problem into different parts, and in parallel it develops these subtasks, and then in parallel create a subplan for each of these subtasks. All is happening in real time in parallel, and finally all of these subplans are merged into a final plan. Again, the agent is equipped with different methodologies and structures that, depending on the use case or the problem it's facing, it can actually decide to employ. And the second really important thing in these reasoning systems is the process for planning and how the agent actually approaches the planning. So here you can see basically a zero reasoning kind of architecture where you have an input and then an output. This is input-output prompting. This is the basic one, okay? Here you start scratching the surface of reasoning. The first one is chain of thought prompting. You give the agent an input, the agent will break it down to sequential tasks as it thinks about the problem. Eventually, it will give you an output. Now, the third one where things get interesting. It's called self-consistency with chain of thought. This is chain of thought, but the agent does it in multiple runs, and then it will see the idea that actually is repeated or the more consistent output from the different runs, and it will decide that this is the best answer to give the user. So this is, it has its own validation process embedded in it. And lastly, the tree of thoughts. And in the tree of thought, it breaks down the problem into the scenarios, the potential outcomes for each step. And based on the structure that it creates in its virtual mind as a tree of thought, it will decide, this is similar to something called the Monte Carlo technique. It will decide in a simulation type thought process. So it will try to simulate a realistic run of the problem it's trying to solve, and it will decide on the probable best actually approach to solve that problem, and then it will give the outcome. So this is interesting, but read something around the Monte Carlo simulation or Monte Carlo technique. It will make much more sense. So the tree of thought is something else, and it's not better or worse than the chain of thought. It's just a different way that if you equip the agent with, it will have multiple ways, as you see here, of addressing a problem. So one other way, if it's easier to look at this, if you are familiar with ChatGPT and reasoning or the thinking, so the effort of that thinking, this is like basically instant, this is little effort, high effort, and this is hard thinking type of effort. Okay, so just an easy way to think about these things. Now, before going out of the reasoning, and you've seen in the architecture, it's adjacent to memory, but one of the things that these systems have to do is self-evaluation. So all of these things we looked at in chain of thought and tree of thought, all of them help and give the model features to get it to self-evaluate, and then detect errors and analyze them, correction and improvement, and then goal-driven reflection. So you need an agent that can do reflection on what it did based on which query that it got from which user and so forth. Again, reading this paper in detail, believe me, will help you make or build much better, smarter, and could be breakthrough type of agents. And here they talk about a different system, which is a reflection system. And that's a system by itself to evaluate the agent, a system that you're creating, and to see what kind of errors you're getting, how the agent is handling them. So this is a system and an idea by itself, and super interesting if you want to build something scalable, smart, and that will stay and remain and compete towards the future. And here you can see a clear architecture for the reasoning system, including the reflection system or the validation system, which is really a subsystem of the reasoning system. So you can see here, this is employing the DPPM, which is decomposition, planning, parallel, and merge. Okay, so the merging for the final plan happens here. And then you go here into things like the chain of thought and other reasoning techniques that we looked at that eventually go back to cycles of reflection that will help the agent to go in loops and really reason through an idea or a question or a query before it responds. And this is a really interesting part. So after explaining the subsystems and the architecture of the agent, here they recommend a multi-agent system. So you can see here they're talking about things like a planning expert, a reflection expert, error handling expert, memory managing expert, and each of them will have its own description and breakdown of the best way to approach that expert. So again, this is something I will not cover, but they go into a good amount of detail of how to build each expert and even how to a certain extent prompt it, create that system prompt for that agent. This is highly recommended part. And here they give you a really nice visual of how these agents interact with each other. So they've created this architecture of the systems operating for each agent, and then how you can actually break down this agent in different perspective through different experts and get those experts to focus on certain tasks or certain parts of the architecture and work with each other to achieve the ultimate outcome of that architecture. Memory system comes here and it's close to the end of this paper, and I will not go through it. Again, it touches on everything when it comes to memory. The limitations, where you use each type of memory, where it's useful, where it's not, and why the memory part is important for building this agentic system or this agent architecture. And finally, we go to the execution system. Again, this is something where they cover things like tools, API integration, multimodal action spaces, visual interface automation. They cover so many areas. So code generation and execution, robotic and physical system control, integration challenges and solution. So they cover the whole thing when it comes to running in concept an execution system that operates in the physical and the virtual world, how that looks and how that actually might work. I hope you learned even a single thing out of this paper. I genuinely decided to go through it just to give these concepts, just an idea sometimes can help someone who's stuck while building or who is discouraged not to start building their own or first agent. I've built voice agents, I've built text agents, normal standard agents, so many types of agents. I've done some of them by coding, some of them by using initn. So this is the future, at least for now. Agents are not there yet, as I clearly mentioned early in the paper, but I think as we progress in this technology, they will become smarter and better and more able. So it's the right time for you actually to get on board and try to build your own agent. Hopefully this helps you. If you're already there, maybe I just introduced you to a paper that is simple, easy, but introduce something that could potentially solve a problem that you are facing. So I hope you got value out of this video. If you did, do not forget to hit that subscribe button if you like to watch more content like this. And if you just enjoyed it, maybe you don't want to subscribe, that's fine. Hit that like button. And with this, thank you for watching and goodbye.
Subscribe to Daddy's channel. Give me the mic.